SDSC provides several different computational clusters. We have HPC systems and massive storage and high-speed networks to facilitate researchers when they come in at whatever level, whether it's running massive simulations or small-scale single-core jobs. We also provide things like data transfer mechanisms and large suite of application stacks to support as many researchers as we can within this. Right now, we run 2 national systems, Gordon and Comet. Comet is a Dell HPC cluster designed around the Dell PowerEdge C-Series servers. One of the nice features of the Dell PowerEdge C-Series servers that we have is that they have 10 gigabit Ethernet ports as part of their management access. This means that we've gone from a typical 1 gigabit management network to a 10 gigabit fabric. When it comes to managing the compute nodes, deploying them and provisioning them, that bandwidth is a huge benefit because it reduces the time to get the operating system and software packages onto the nodes when nodes are taken out of service or for updating. It also means that all of the control tasks for starting jobs and stopping them and administrative actions happen at a much faster rate. Comet's management fabric is powered by Dell N-Series 10 gigabit Ethernet switches. The N-Series switch includes the capability for VLANs and tagging, which is a technical term that allows us to isolate the traffic between different virtual clusters. This is key so that virtual clusters, when they're operating, can have their own traffic lanes without seeing each other's packets or messages. SDSC uses Ethernet heavily as our primary storage fabric. It's because it's a flexible network technology that integrates well outside of the Supercomputing Center. And it also allows us on our storage infrastructure to use Ethernet to bring connections from different storage resources into separate clusters. And we can aggregate our storage and target where it gets deployed to. Within the virtual cluster environment, the Dell Ethernet fabric also provides simplified access between nodes of the virtual cluster. For nodes that don't require the RDMA fabric or where the administrators aren't familiar enough with it to provision and deploy the infrastructure, they can use the existing Dell Ethernet fabric with little effort.
The University of Colorado Boulder is one of the top public research universities. Research computing at CU provides computational resources to support all types of research that have large-scale computational needs.
Here at CU, we support many dozens of research groups from nearly every department on campus. And based on that, as we were thinking about the design of Summit, architects from Intel and Dell EMC helped us to determine what sorts of components would provide a much wider range of different capabilities in terms of computation, in terms of the network, in terms of the storage, to support just a vastly greater range of applications.
The architecture within Summit consists of 4 computational partitions. There's what we call the Haswell partition, which is the Dell EMC PowerEdge C6320 partition of the system. That's based on the Intel Xeon Haswell architecture. The E52680V3 processor provides good balance not only in price or performance, but also in clock speed versus number of cores per processor. The second partition of Summit is a GPU accelerated partition based on the Dell EMC PowerEdge C4130 architecture. The third is a high memory component, and this is largely to service some of our partner institutions that really need a lot of memory in one box. And then the fourth is the Intel Xeon Phi Knights Landing platform, which is a CPU processor, not a co-processing architecture. Rather than having to worry about going out to an accelerator, they can just program right on the machine. So we're really excited to see that be a simpler architecture for our users to program against. All of the compute sits on the Intel OmniPath architecture fabric that we've built up as the interconnect that provides 100 gigabit per second connectivity to each host. New technology, like the Intel OmniPath architecture, like the Intel Xeon Phi Knights Landing, provide cutting-edge performance. Summit provides more than twice the floating point performance in about half the data center space, power, and cooling when compared to our previous generation system. We're expecting about 400 teraflops of performance from this machine.
Summit will definitely have enough juice to run the majority of big problems that our researchers need to get into.
I study galaxy formation, and we run these simulations for a long time. They take 100,000 to 1 million CPU hours. Fortunately, with a system like Summit, you're running simulations on 512 to 1,000 cores. With Summit, we can build more realistic galaxy simulations at higher resolution and with new physics.
Quantum physics is everywhere in our life. It describes pretty much every experimentally understood phenomenon. Your camera, the phone, computers, internet has some kind of basis in quantum physics. Having Summit, I can answer questions about high-energy physics and get more precise predictions than what was possible without Summit.
We do research on numerical simulations of turbulent flows. We have projects on combustion for propulsion engines, combustion for wildfires, geophysical turbulence, particularly in the ocean. Summit will allow us to better use computational fluid dynamics, and that's largely because of its increased computational capabilities. I think it's rare to have such a powerful computer so readily accessible.
What excites me most is that we want to bring researchers together and they focus on their research and we focus on providing the computational infrastructure for them.
The thing that I love about HPC is when somebody's using one of our systems and they come up with a cool new result or they make a fantastic new discovery that just would have been completely out of range otherwise. It's awesome.
The Ohio Supercomputer Center is made available for the entire university system in Ohio, as well as Ohio industry. In the commercial space, we're really looking at modeling and simulation to improve product design, make things better, cheaper, faster. On the academic side, we support all aspects of science and engineering, everything from nuclear engineering, aerospace engineering, to biology and medicine. They're customers who need high-performance computing services. Our new Dell EMC Intel cluster, Owens, provides a robust increase in the overall capacity for the center.
For the architecture of the Owens cluster, we've built the systems based on the Dell EMC PowerEdge 6320 servers. These include the Intel Xeon E5 2680V4 processors. So we picked that particular Intel processor because of the superior memory bandwidth and the superior floating point performance. It also has a broad set of HPC applications that are already well supported on the platform. The Intel processors support the AVX2 instruction set. And this will be a good first step for our users towards the Intel Xeon Phi processors, which introduce an even wider vector instruction set. The total number of cores in the system is a little over 23,000. The peak performance of the Owens cluster is 750 teraflops, 4 times the peak performance when we compare it to the existing systems. With the Dell EMC and Intel system, researchers will be able to run larger problems and it will have significant benefits for their research.
We do mostly molecular dynamics simulations on polymer materials. So polymers are these long chain molecules composed of the same chemical unit repeated many times. And one of our main projects is to create easier, cheaper, safer battery materials. We often have the problem that we have to wait long simulation times before things happen. So we're often hitting the wall time of 4 days. And so now moving to Owens, we can literally run the same simulation twice as fast. It really lets us focus all of our energy on the scientific questions we want to address that could impact people's lives.
We're very excited to deliver this capacity to our customers. We have clients like Ray Lito at TotalSim, where OSC provides a competitive advantage for Ray is an ability for him to run larger simulations for computational fluid dynamics.
TotalSim is mostly an aerodynamic consulting company, but we do most of our aerodynamics in computational fluid dynamics, or CFD. CFD is highly dependent on high-performance computing systems to get this work done in a timely fashion. One of the great things about the new cluster here at OSC Owens is just the sheer core count and memory is going to allow us to, in the same time period we could on the old clusters, run a higher fidelity model, larger models, more models, and get more work done in the same time period. It allows us to think bigger, think in more detail, and think about doing these things that we had previously dismissed because they were just too time consuming.
The new Owens cluster is a much more efficient system from the perspective of how much power it takes for the amount of performance that we get out of the system. We installed the Owens cluster in the same footprint where an older system was previously installed. And they required a very similar amount of power, except the Owens cluster has about 25 times the peak performance of the old system. So that's a remarkable improvement in efficiency.
Having an integrated solution with Dell EMC and Intel allows us to provide higher reliability for our customers. We know we're getting best-of-breed solutions in the marketplace. We expect and we get higher reliability, higher levels of service, and an opportunity for us to not focus as much on the details of our hardware and to focus more on what our customers need.
Every department on campus is using a cluster to do some type of research. A cluster like this is what is required today to do modern science.
The University of Alabama at Birmingham is a comprehensive research university. This is a young, nimble research university, highly ranked. We bring in close to $500 million in NIH funding for research every year. Our intent is to change the world, and nothing less than that. So we are very intent on genomics research, cryptography research, brain mapping, personalized medicine.
Personalized medicine is creating individualized therapies to treat not only the disease, but to treat the disease that any particular patient has. When you look at the data that we work with, especially human genomic sequence data, it's impossible to analyze that using the past resources that we have.
The data that I work with is very large. We're talking gigabytes to terabytes in size, and a normal desktop computer would take months, even years, to analyze just one project.
The computer resources that we have available now through our high-performance computing system named Chiaha, those are able to now analyze those data in a matter of hours, where it would have taken days or weeks before.
The cluster is essential not only for the speed of the analysis, but also to be able to support everyone here at UAB, from the clinicians on the medical side to the researchers here on the research side.
I study how it is that the brain is changed by experience. To be able to help people who have loss of central vision, we use functional MRI to look at the level of brain activity over time. And we can look at it in every part of the brain simultaneously, so we get an enormous amount of data out of this method. It would take about 24 hours to do a simple processing stream on one brain. And now, with the new cluster, with Chiha, we can do 100 brains in less than the same amount of time. It's absolutely critical that we have a cluster like Chiha to be able to do this kind of work, because that just makes everything that we do possible that wasn't possible before.
In looking at high-performance computing and looking at empowering greatness in others, we chose Dell EMC and Intel to work with us to deploy this system, and it's been a great partnership.
The current configuration of Chiha has about 2,300 cores, and the cluster consists of two types of Dell EMC servers, the Dell EMC R630 and the DSS 1500 servers. And each of the servers has the Intel E5 2680 processors. This new cluster essentially increases our computational capability by 10 to 11 folds. We had a 10 teraflop computer earlier, now we have a 110 teraflops computer. We also have a couple of nodes with the newer generation Intel Xeon 5 accelerator cards. This allows us to get our users ready when we have the next generation of the Intel many-core processors readily available. We can easily get them order of magnitude increase in their performance by taking advantage of this architecture.
The research computing infrastructure at UAB is spectacular, but the physical infrastructure is not going to work unless you have the really great personnel to help people do what can be done with that wonderful piece of equipment.
Designing a cluster to meet a large number of user requirements is always a challenge. It's a major collaborative effort between Dell EMC and Intel. They have been phenomenal in setting up the cluster from rack and stack to cabling it to configuring it. We also put in training.
We're trying to remove those barriers and automate processes to take tasks off of faculty members so they can focus on solving these very difficult challenges. We're looking at the most difficult problems facing mankind, and we're trying to solve those problems for the benefit of the entire planet.
The University of Connecticut is a top 20 public research university. It's a land-grant institution. It has about 35,000 students and about 6,000 faculty and staff.
Our missions are to educate students and prepare them for the workforce. Our second mission is to conduct state-of-the-art research and to create new knowledge. And our third mission is to engage industry and to have an impact. The climate at the University of Connecticut now to integrate those missions has just been really tremendous. High-performance computing is absolutely critical to what we're doing.
Research computing, in large part, was historically very individually researcher-focused. They built all their own infrastructure and they maintained all their own infrastructure. When the university began to make central investments in infrastructure, that freed up researchers and graduate students to focus on the actual place where they add the maximum value, which is in pursuit of science.
Today, we've deployed several hundred Dell EMC PowerEdge M630 servers to be the core of our storage HPC cluster. The Dell PowerEdge M630 servers has been a really good sweet spot for us. It allows us to deploy multiple different workloads in the same environment. It's also a platform that is very easy for us to manage. But today, we're at about 6,000 cores. Intel processors for us has always been the logical choice. Intel is a leader in the market for processors for high-performance computing. We selected the Intel Xeon E5 2690 Haswell processor, which met the most use cases possible in terms of how many cores it has and how fast the clock speed is. We deployed several thousand of those recently, and we've been very happy with that processor. They're compatible with our previous versions of our Intel processors. There are nice new features like the AVX2 extensions. Faculty have been very happy using the cluster. They've been able to take the results from weeks down to days or hours. We recently purchased 2 Dell EMC PowerEdge R730 servers, each with 2 Intel Xeon Phi coprocessors. There is a lot of excitement around the Xeon Phi processor. In certain workloads, our faculty believe that they can achieve a great speed up due to the many core architecture. Dell EMC and Intel have helped us to deploy high-performance computing at large scale with relatively limited local resources and to be successful so that our faculty are successful.
We've gotten tremendous feedback from all the faculty we've been hiring about the capabilities we've been able to provide them in high-performance computing.
The problems that we address today are either computationally very intensive or they involve a lot of data. So the high-performance computing enables us to solve so-called intractable problems faster than what would be otherwise possible. For example, the simulation project led by Manos in forecasting weather models.
Predicting weather, it's not possible without high-performance computing. When Superstorm Sandy hit Connecticut, we developed a model, a preliminary model, an early-stage model of outage prediction based on Storm Irene. We combined the weather forecast with our storm outage model, and through this, we provided quite accurate forecasts of the location of outages and the timing. We cannot avoid Mother Nature hitting our infrastructure. All we can do is better plan. Our vision is to save, for each storm, millions of dollars for our utilities.
We're really committed to building the capability in the HPC, and the excellent partnership we have with Dell EMC and Intel in building this system has been one of our largest successes in the last couple of years. And if I went around and I named all the faculty who are using the HPC facility, and you look at their research and you see the impact of that research, it's just tremendous.
We saw that there was a need to create a system where data came first. TAC is a center which is part of a group called Exceed, funded by the National Science Foundation to support and educate people in how to use advanced computing to enable all fields of research that have computational challenges, including data science. Wrangler was our first delivery of an at-scale Hadoop system from Dell EMC, Intel, and Cloudera Technologies to tackle the diverse workloads that researchers across the country were not able to do because of the I/O limitations or the storage limitations of the system.
We had a number of researchers who had big data problems that really couldn't be solved with either our existing infrastructure or other systems around the country. The users on Wrangler, they tend to have more diverse data sets, lots of different kinds of data points, data with a lot of complex internal structure.
We do a lot of work with unstructured data, with analysis of data from the web. Wrangler is perfectly suited to my research because it's the first NSF big supercomputer that has a really big focus on supporting Hadoop and Spark environments. So we have a tool called DRAT, the Distributed Release Audit Tool, that we've been building that does code auditing and analysis on very large corpuses. And a particular government program asked us to use DRAT to do an open source code audit. And so we were running that for months on a cloud provider, and we were unable to get results out of that because of storage, processing time. We just couldn't get the code to complete there. And we brought that over to Wrangler, and we were able to complete that code analysis in about 2 weeks.
For researchers to do their big data analytics that are data intensive, the compute part of Wrangler uses Dell EMC PowerEdge R630 servers running Intel Xeon E5 2680 V3 processors. With the higher performance Intel processors, people are now able to answer questions that they previously couldn't on a traditional supercomputer, simply because of the computational power of the new processors.
Big data is inescapable. When I heard Wrangler was using Intel processors, using the flash storage, it's perfect for big data environments.
So the centerpiece for many people in Wrangler is our large-scale flash file system. The solution that we got by combining the Dell hardware with the EMC DSSD D5 was a very compact rack-scale computing environment.
The Dell EMC DSSD flash storage is connected to every one of the nodes with PCIe external connections, which provides a lower latency, more IOPS, and in many cases more throughput than what you would get in a lot of HPC clusters.
Being PCI attached allows us to project that storage into whatever problem environment you have, whether that be a high transactional rate database, whether that be a NoSQL Hadoop solution, or running extraction, transformation, and loading scripts through environments like R, Python, or SAS. People are now able to migrate from a system where you have a slower shared infrastructure to one that is a more tunable infrastructure using DSSD flash storage. The DSSD D5 plugin for Hadoop couples with the Cloudera environment to allow us to give Hadoop users the full benefit of the throughput and IOPS possible with the flash storage, which has been described by many people as limitless I/O capacity. We have seen anywhere from a factor of 5 to 50 performance improvement. We've also seen applications going from taking weeks to nearly months to run, to running in less than 4 to 6 hours, and that's due to the low latency and high throughput of the flash storage. We can onboard people to the system and very quickly allow them to understand that the problems they never thought of being able to address can be easily tackled and enable research that nobody thought was possible before.
I think what excites me most about my current research is just the ease and ability to understand data. I want to grab all the computer vision algorithms. I want to grab all the speech-to-text algorithms. I want to grab everything that extracts information from any type of content and make it easy for people to use. So in an environment like Wrangler, just making sense of that data, extracting information from it, turning it into knowledge, that's what's exciting to me.